critical over the flat plate where the boundary layers are kerosene at T equals 68 degrees Fahrenheit begins to transition from laminar to turbulent flow. And we'll take that density, it's 1.58 plus per cubic. Kerosene that's flowing over here. You've got this kerosene that's flowing over here, right? And so as it hits this front bit right here, you get this boundary layer that starts to form, right? You got that sort of thing going, where all this stuff up here is just free stream, right? Free stream velocity. And you have this little delta, and delta is that boundary layer thickness, right? And so now let's say, for the sake of argument, our critical Epps length is like right here, right? So everything before this is perfectly laminar, okay? And you get a velocity profile that's pretty nice, pretty well behaved, right? It's like what you saw in that first few sets of homework, right? Where you had that like velocity gradient sort of thing, right? You know what I'm talking about? But as soon as you get past this, whoa, what the hell is that? Someone jackhammering up above us? What the fuck? Anyway, ooh, probably shouldn't drop enough on. Anyway, okay. Anyway, hopefully HP doesn't watch a video that far into the. Anyway, okay. So like I was saying, past this critical point. Okay. Okay, yeah. Well, hopefully that doesn't keep going. Anyway, this is a quick recitation. I won't spiel too much. But okay, so past this critical Epps length, right? Everything's turbulent past this. So you get a velocity gradient that's like super nasty. It looks like that. All right. You get something like that, right? And so we want to know what this critical Epps length is so that we can design stuff so that you can keep it laminar. Hey, can all you guys just kind of keep it down a little bit? Don't you guys have like an exam right after this or something like that? Or like another midterm, something like that? You already did it? Oh, quit talking about it. Who cares? You're done. Who cares? You already took the thing. Who gives a shut up. Anyway. So you want to find this critical Epps length so you can design your plate or your airfoil in such a way that you can keep it laminar if you want, right? If you want to deal with easier math, you can keep it laminar. So what's our transition point? And you guys have probably talked about this. It's when your Reynolds number at some X location is about 500,000. Right? So this is pretty easy. We know how to calculate Reynolds number, right? A Reynolds number with respect to X. It's just in this form, right? We're going to use kinematic viscosity because that's easier. It's your velocity times whatever your X location is divided by nu. All right? Texting you, go away. My mom keeps texting me. Stop, mom. Jeez. Anyway, yeah. So this one's pretty easy. So we want to solve for this X right here. So just plug in. Yeah, 500,000 equals what? 4 times X critical over 25.4 times 10 to negative 6. All right. And so with that, pretty easy. Just plug and chug. Your XCR equals 3.175 feet. And literally that's it for problem 1. That's it. See anything else I want to talk about here? So basically, this is a good number to know because, like I was saying, if you can constrict your whatever thing you're trying to design to like below this level, then you can keep everything in the laminar flow regime, right? You don't have to deal with any turbulent boundary layers, nothing like that. And the math gets a lot more simple, right? As I'm sure you guys have seen, you have pretty nasty equations for when stuff gets turbulent, whatever. Any questions with that one? Pretty chill. Cool. All right, in that case, let's move on to question 2, which is slightly more involved. But anyway, so here's problem 2, okay? So we've got the chart shown has the total drag coefficient based on frontal area of 0.5. And this one's kind of important. If you guys are talking in the back, I would recommend watching this one a little bit. Okay. The frontal area is 9 square meters. Find the total drag if it's going 30 meters per second. Assume that most of the friction drag comes from the sides and top of the trailer. Trailer 16 meters long, 3 meters high, and 2.5 meters wide. Find the friction drag at 30 meters per second, still going 30. And then part C is a discussion thing. We'll get to it in a sec. Okay, so for part A, all right. So we want to find the total drag, right? We know CD equals 0.85 and A equals 9 square meters. All right. Did I give you? I didn't give you everything else. So we also have rho equals 1.225. And then mu is 1.825. All right, so this is kind of a nice problem because it really shows you like why you were doing the Buckingham Pi stuff from the jump. All right, have you guys talked about drag coefficients, things like that? Okay, so you remember, right? Um, whenever you'd be doing your pi group stuff and you'd be doing some pi, like pi 3 equals like some force over rho v squared L squared, right? You'd keep getting something like that, right? This is the general form for a force coefficient, all right? And now the only thing we do in this case, right? One drag coefficient. Right? And so this is literally just CD. That's our pi group. We're calling that CD equals D over except, and D is our drag force, right? Force of drag. Except we do a little funny business for this one just by convention, right? We call it 1/2 rho V squared times some area, right? Because a length squared is just an area, so that's fine. And then this 1/2 rho V squared. Remember back to your Bernoulli's equation when you'd have like P plus 1/2 rho V squared plus rho GH, all things in terms of pressure. This is called this quantity right here is 1/2 rho V squared. It's called dynamic pressure. Okay, so that's why we throw that 1/2 in there because it's nice to have everything all in one little tight thing, right? So if you have your dynamic pressure, you can just plug it into the bottom. Actually, in a lot of like air applications, this 1/2 rho V squared just gets over 2A. Kinds of drag. Okay. It was 4217.06 newtons. All right. And this is important to note. This is the total drag, right? So this doesn't discriminate what kinds of drag are involved here, right? Because there's different kinds. We'll get to it at the end, but there's different kinds of drag, right? This doesn't break those down. This is literally just saying if I had this truck in a wind tunnel and had a force meter on it, this is how much force I'm feeling from the air, period, right? We can't, from this number alone, we can't differentiate which components of drag are acting. We just know this is what it's feeling, right? Which is useful in a lot of cases. But anyway, okay, so now for part B, assume that most of the friction drag comes from the sides and top of the trailer. 16 meters long, 3 meters, and 2.5 wide. Find friction drag at 30 meters, so it's still going 30 meters per second. Okay, so for part B, the drag coefficient is the same form, where CDF equals drag due to friction. And you'll hear this called like friction drag, skin friction drag, drag due to friction. It's all the same stuff. It's all friction. It's the same thing. It's 1/2 rho V squared, except now the area we're talking about is usually denoted S wet. It's the wetted area, And for the scope of this class, you can think about it like the surface area of the object that you're worried about, right? So in this case, what's the area getting? Okay, so I will give you a little about it. So as from what I've been told, this comes from an old like aviation thing where when they'd be making like scale models of stuff and they wanted to figure out which surfaces contributed to like skin friction drag, they'd literally take their little scale model and they'd have like a bucket of dyed water and you just dip the thing in the water, pull it out, and whatever surfaces were wet is what contributed to skin friction drag. So you can think of it as just like a surface area thing, but once you get into like actual modeling stuff, it's not like quite that simple. But for this case, just think of it as like the surface area of the object in question that you're worried about. So in this case, we want to worry about the surface area of the two sides of the truck and the top of the truck, or the trailer, I guess, whatever. So S wet is just 2 times where the sides, it's like 16 by times 3 plus the top, 16 times 2.5. So the S wet equals 136 square meters. And go, all right, well, that's fine, right? So we found the wetted area, but I still need to know my actual skin friction drag coefficient. And whenever you hear some sort of skin friction drag coefficient, you better be thinking, I need to find a Reynolds number because the two things go hand in hand. All right. If you got a skin friction, Reynolds number. Okay, those two things. So let's go and do that. So what we're gonna do, we're gonna find the REL, the Reynolds number with respect to the whole length of the trailer. Okay. Um, and that's because like previously we found that critical X length, that critical Reynolds number, REX, where it's just at that transition point. If you take the Reynolds number for the full length of whatever object you're talking about, that full Reynolds number is what essentially like governs the flow of like governs the behavior of the flow for that whole object. So you want to, in this case, we want to take the full Reynolds number so we can tell if it's turbulent, if it's laminar, if it's mixed, whatever. So let's do that. And so this is just usual rho v L over mu. And so this is, times 30 times 16 over 1.825 times 10 to the fifth. Okay, you end up getting REL, Reynolds number with respect to the full length of the trailer. It's like 32.22 times 10 to the sixth. So 32.22 million is the Reynolds number. So obviously it's very turbulent, right? And don't be alarmed if you get a really big Reynolds number like this. In external flows, just by the sheer mathematics of what's going on, you're going to get really big Reynolds numbers, right? Usually have, moderately, like a couple meters length, but like a really fast velocity and a really small viscosity. So you're dividing by a tiny number and multiplying on top by a couple fairly big numbers. So you get really big Reynolds numbers here, but it's turbulent. So anyway, we're going to assume mixed boundary layer, right? And I say that because there's nothing telling us in this problem that the flow is turbulent from the very beginning. We just have to find that out on our own. So we can assume that the boundary layer starts laminar, and then like we found in problem 1, it transitions naturally into that turbulence, right? There's nothing saying otherwise, so we just assume that it's that case. So now we go look at our set of equations that we have for skin friction, and we pick the one for a mixed boundary layer, which if you haven't seen this equation already, you will. You will be given this equation. You don't need to like, I would recommend writing this down, but you don't have to like derive this. You don't have to pluck this out of thin air. Right, and that's like log base 10, right? Not natural log. Right? That'll give you a really bad answer. But it's 0.455 over log base 10 of your Reynolds number to 2.58 power minus 1700 over the Reynolds number. And I believe that 1700 over REL, that's like taking into account the laminar part. Don't quote me on that. Right. So at least here. Anyway. But now you've got everything. You've got the Reynolds number. It's really the only thing you need. So just solve straight up for your drag coefficient. And this will be a small number, which of course is good. 2.45. Times 10 to the negative 3. Okay. Really little number. So now again, let's go plug in, solve for drag. Right, plug everything in. You get DF is 183.98. And boom, there you go. There's that one. Okay, and obviously, whoa, real shocker. It's a lot smaller. Okay, which is fine. That's to be expected, right? Just the viscous force of air pulling on the truck isn't going to be that high. But I mean, 200 newtons is not insignificant, right? But let's get to part C, which part C is just an explaining one. So I'm not going to write too much stuff about it. So first off, though, C, big part of it, percentage of drag from friction. Okay, so this is literally just dF over D. It was like 4.36%, right? It's like I was saying, it's a small portion. So I could sit here and spiel all day about stuff like this, okay? But so what's another source of drag? Okay, so obviously we see this and we think clearly friction is not the main player. So who's the bad guy, right? Who's the bad guy? Well, common theme in fluids. What's driving everything? Who's the HBIC, right? Head bitch in charge. That's what that means. It's pressure, okay? Pressure drag. Underline that bad boy. Okay, pressure drag is the bad guy. That's what's driving all this thing. Okay. And you think about it like this. All right. So you've got our truck up here. Okay. And as this is punching this hole, right? Obviously it's going that way with some velocity. As it's punching this hole through the air, you've got all this flow coming up over the top. It's cool. It's whatever. It's having a good time. Right. It's fine. It's all the airflow. But at the very back of this truck, right, because you just punched a huge hole in the air as you're going 30 meters per second, whatever, you've got a huge area of low pressure back here. Okay. And so what do we know happens with fluids when they're at a high pressure and they meet an area of lower pressure? They want to go to that area. Okay. And so what you get here is you get all of these rear end vortices, right? All this turbulence back here, turbulent weight, right? And so not only do you have that contributing to all the drag and whatnot, you literally this area of low pressure right here is pulling back on the truck. All right. So you're getting a bunch of drag from that. All right. So that's the main player, pressure drag. And you can also think about it like this too. I'll since we have a little more time, I'd relate this to like think about an airfoil. Okay. This is kind of the crux of boundary layer theory. Okay. Imagine you've got an airfoil here. All right. Whoa, so much easier to draw an airfoil on a board. Anyway, imagine that's an airfoil. It's at like 0 degrees. Okay. And so you've got this air flowing over, no problem, right? It's having a good time. Again, it's having a good time, right? It's coming over, it's staying attached, it's doing good, right? Technically speaking, since you have fast airflow going over both surfaces, you have areas of low pressure on both sides, but it's fine. You know, they're equal pressure to each other. So you get no drag, no lift, nothing like that. You get a little bit of low pressure back here just because you're still punching a hole in the air. You can't get away from that. But imagine, this is like if you're in your Gulf Stream, just cruising at like 30,000 feet, drinking champagne with your buddies, right? What if your pilot's like, just have a good time, right? And so he pulls back on the stick like crazy, okay? And you get a super dummy crazy high angle of attack. You got something like that, right? Just going real wild with it. So, the air coming down below, that's cool. It's still staying attached. It's just smacking it, it's punching into it. Kind of sucks, but it's staying there. It's cool. But the air coming up over, right? It wants to try and stay attached to the surface because that's what air wants to do, right? Because of viscosity, like we just saw, right? That boundary layer stuff, it wants to stay sucked on to the surface because of the no slip condition, because of viscosity, things like that. It wants to stay there. But there's such a nasty angle that it's trying. It just can't. It comes off at the very end. So we say the boundary layer has separated. And once again, right, you get an area of low pressure back here. So you get all these wisps and stuff's going crazy, right? So you still have high pressure on this bottom part, but everywhere else, right? Everywhere else, this is all just free stream, right? So this is just atmospheric pressure right up there. So what just happened, right? If you want your lift to be acting in that direction, well, you just got rid of all of the low pressure that's pushing you upwards. That's not good. So what you just do, you just stalled your plane. Your boundary layer is separated. You get all this pressure drag back here. So what are you doing? You're increasing drag and decreasing lift. All right. That's the crux of this whole thing. Pressure drag is bad. You know what's called an adverse pressure gradient on this back side. Go look it up if you want. Where the rate of change of pressure is you're increasing pressure. Okay. You don't like that. It's bad. It's adverse, what they say. So anyway, that's really bad. So that's how like an aircraft stalls. All right. Oh, and the last thing, okay. So you notice, right, in this really high Reynolds number flow, our drag due to friction is really, really low. All right. And that's a good indicator of actually what's going on with this flow regime, right? When we have such a huge Reynolds number like this, think about it like this, okay? What's the Reynolds number really telling us? Well, we have some rho VL divided by mu, all right? So we've got some like momentum velocity forces on top divided by some like viscosity thing down below. So it's like the ratio between momentum and viscosity, right? So if you have a really fast moving flow or a really long object, whatever, you get a really huge Reynolds number, and you can say, well, obviously, like the viscosity isn't playing that big of a role, right? And you can back that up. You can go do and calculate the friction of it. So you can say, okay, well, at really high Reynolds numbers, we can kind of throw out the friction part of it. So that's why if you go and take an aero class, for the first like 3 quarters of the class, you're not touching friction. You're not doing nothing like that because hey, it's only 4% of the drag in this high Reynolds number regime. On the opposite side of that, though, if you get a Reynolds number where say you're moving through something really viscous like honey, you're like driving, you're trying to swim through honey, okay? Super, super thick, super viscous. So your velocity is going to be really low, okay? And your viscosity is going to be really high. So obviously, the viscous forces are what's going to be driving that drag. You can go back it up with math. You can do whatever. So at the end of the day, that's why it's a fairly good approximation when you get to your upper level classes. If you're dealing with some friction, you say, oh, well, let's assume let's assume there's no friction because you have a really fast flow and it's air, really low viscosity. Just, yeah, at the end of the day, you can throw it out. If you just want a big overall general look at what's going down, you can throw it out and be like, hey, let's just look at the total drag without any viscosity and see what happens. If you want to go deeper, you can. But as far as approximations go, it ain't too bad. That's kind of all I want to say about boundary layer theory, stuff like that. Probably a little deeper of a dive than what a lot of you guys care about, but whatever. We're here for a good time, right? Anyway. All right. Any questions with that? Pretty much everything I wanted to really go over. Anything. All right. Everybody cool? Reminder, next week is like a review session. do with that what you want. If you want to show up, like I'll still take attendance, obviously, but if you've got like a freebie, be my guest, right? Anyway, all right. And online, if you guys have any questions, shoot me an email. Have a good one.